Welcome everyone to lesson 2.13 from Precalculus, which is all about exponential and logarithmic equations and inequalities. This is one of my favorites, so let's get started. Our first and only real big idea for this lesson is a reiteration from before, the fact that exponential and logarithmic functions are one-to-one. So this property means that for every input, there's a unique output, which also works around. Every output has a unique input. So we can essentially start to use logarithms and exponentials as operators in our equations. I don't know technically if that would be the correct way to put it, but that's what makes sense to me, and I hope that's what makes sense to you. So let's dive into what that actually means. So if I have a function, or I have an equation rather, where x equals y, then it has to be true that log base a of the left side has to equal log base a of the right side, as long as the inside of the logarithms, as long as the equation itself, those values are greater than 0. So if I have like 4 is equal to 2 squared, and I take the logarithm base 5 of both sides, it would still hold true. It would still be a true equation. Same thing is true for exponentials. If I have x is equal to y, I can raise a number. It doesn't matter what the number is, as long as the number is not 0 or 1. That gets a little weird, and positive. Let's keep it in the realm we've been working with, right? Then I can raise that number to the power of the left side and set it equal to that same number to the power of the right side. So this is going to help us solve equations going back and forth. So we can go forwards or backwards with these properties. These are essentially identities. I want to put like an asterisk on that because we have like some things we have to make sure is true, like the a has to be positive for all of these. For the logarithms, like the x and the y have to be positive, but for our intents and purposes, we're going to use them like identities when we solve equations. Speaking of, let's solve some equations. So let's start with this first one here. We have 2 logarithms being added together is equal to a third logarithm. So first thing I notice is that all of the bases are the same. That's a plus. And we have a lot of logarithms. So my method I'm going to tackle this with is I'm going to condense these 2 logarithms here. Remember, when we have addition on the outside, it turns into multiplication on the inside. So we actually have log base 2 of x squared plus 7x is equal to log base 2 of 60. And now, since I have a logarithm equal to a logarithm of the same base, I can set the arguments of the insides equal to each other. So then x squared plus 7x equals 60 has to be true. Awesome. Now we can solve this. It's a quadratic, so I would move the 60 to the left-hand side and then factor. In fact, I'm going to go ahead and skip that step, and I already know that that is going to be x plus 12 times x minus 5 is equal to 0. So we have x is equal to negative 12 or positive 5. Now, for logarithms, you really need to check your solutions. We are now dealing with equations that have, or functions rather, that have restricted domains. Logarithms only work when their argument or their inside is positive. So just because you have a negative number here doesn't mean it's off the charts. It might not work. You have to plug it into the logarithms to see if it will. Because if we have this plus here, well, this argument here could be negative, anything larger than negative 7. But I digress. Negative 12 doesn't work in this logarithm, nor does it work in that logarithm. So negative 12 doesn't work. 5, though, 5 works here and 5 works here, so 5 is okay. So our one and only solution is x equals 5. So you got to remember to check for logarithmic equations, something you really haven't had to do a whole lot of before. This also comes up with radicals. If you're solving equations with radicals, you'd have to check your work, because sometimes you might get answers where the math gives you an answer, but it doesn't technically work out. Here we have another logarithm is equal to a logarithm, but we have this 3. This 3 is not a logarithm, though. We don't really have a rule for combining non-logarithmic expressions and logarithmic expressions. So we need to instead move this logarithm to the right-hand side. So what that would look like is 3 equals log base 2 of 5 plus log base 2 of x plus 7. We have addition with logarithms. That turns into multiplication on the inside. So we have 3 is equal to log base 2 of 5x plus 35. And now we don't have a logarithm is equal to a logarithm. Well, before we would say we were rearranging the equation, and technically that is what could happen. We could say that we're rearranging the equation, and rearranging the equation would give us 2 to the third power is equal to 5x plus 35. And that is true. It's 100% true to do that. And I don't want to discourage you from doing that. But let's think of it as another way. Let's try to use those one-to-one properties just so we get more familiar with these one-to-one properties and they don't feel as weird to us. Sometimes we'll end up with weird equations and we won't know how to proceed unless we expand our toolboxes and expand our minds a little bit. So instead of thinking that we're rearranging the equation, what if I take the left and right side and I say I want to turn this into 2 to the power of the left is equal to 2 to the power of the right? That's an interesting thought. What happens is the 2 and the log base 2 over here cancel, leaving you with just the argument, and then you get your 2 to the third. So there's another way to get to the same idea without having to rely on the same rules. So if you end up with a unique equation that your way of thinking doesn't necessarily work, doesn't mean that there isn't another way that would also work. That would give you an equivalent way of going about it. So I digress. We had all that. 2 to the power of 3 is 8, so we have 8 is equal to 5x plus 35. We subtract 35 from both sides, which gives us 27. Negative 27 is equal to 5x, which means that x is equal to negative 27 fifths. Now we have to check this. So negative 27 fifths is negative 5.2 if you convert it to a decimal. So that might help with your checking if you have like a fraction. Converting it to a decimal to check might be useful for you. The only logarithm that has an argument that has a variable is this one here, and we're fine as long as we're plugging in something that is greater than negative 7, and negative 5.2 is greater than negative 7, so this is a correct solution. All right, so those were logarithmic equations, super fun. What about exponential equations? And I have 2 exponential equations here that are very, very similar, but have very different solutions, so I can highlight some important information for you. So first and foremost, when you're solving with an exponential, typically you're going to try to get that exponential alone. So we're going to divide by 3 on both sides. We're going to get 2 to the power of x plus 2 is equal to 4. If you have a nice exponential, solve them in the way that you would before. I mean, why not, right? So 4 is 2 squared, 2 to the power of x plus 2. Well, exponentials are 1 to 1. This means that x plus 2 has to equal 2, or x is equal to 0. If I plug that back in, 2 to the power of 0 plus 2, that's 4. 4 times 3 is 12. That works out. If I wanted to instead use a logarithm, I would end up with the same answer. I could instead, from this step, go to log base 2 of 2 to the power of x plus 2 is equal to log base 2 of 4. Well, I know from my exponent identities that the power rule would apply, so this would be x plus 2 times log base 2 of 2 is equal to log base 2 of 4. Log base 2 of 2 is 1. Log base 2 of 4 is 2, so I end up with x plus 2 is equal to 2. That looks familiar. The answer is 0, right? So you have multiple tools in your tool belt now to go about equations, and there might be ways where you can't use the one that looks a little bit easier. You might have to use something like the one we did over here. And in fact, if you can't write it nice and neat, you kind of have to. So if I look here, the difference is we're not dividing by 3, right? So I would personally take the logarithm base 2 of both sides, which would be equivalent to rearranging the equation in this case. log base 2 of 2 to the power of x plus 2 is equal to log base 2 of 12. Well, this power rule, x plus 2 times log base 2 of 2 is equal to log base 2 of 12. This turns into a 1, but log base 2 of 12 is not a nice number. It is an irrational decimal. So we don't need the parentheses anymore. We have x plus 2 is equal to log base 2 of 12. And it is a number. It's okay to leave it as that because it is a number. We would subtract x is equal to log base 2 of 12 minus 2. For exponentials, we don't have to check the domain because exponentials domain is negative infinity to positive infinity. There's not that restriction that logarithms have. So this would be the correct answer in this case as an exact answer. If you wanted an approximate, you could use what you know about logarithms to find out what the approximate value of log base 2 of 12 is, and then subtract 2 from it. Here is where we get another one of those weird answers, but it's only really weird if you want it to be weird. What do I mean by that? Well, let's go about solving this and how you would go about it, or how I would go about it anyway. X plus 6 is equal to negative 1. I would raise 10 to the power, put 10 and raise it to the power of the left and right sides. So 10 to the power of log, that's not log, of log x plus 6 is equal to 10 to the power of negative 1. So we have x plus 6 is equal to 0.1. It could be 1 over 10. That's perfectly fine. I think it's a little bit easier to see what the answer is going to be with 0.1. X is equal to negative 5.9. That's not bad. You can use your calculator to solve this. If you have these types of questions on a calculator part of an exam, you can make the left side y1, the right side y2, and see where they intersect. And that is arguably the easiest thing to do. The one problem you'll have is if you're looking for an exact answer, like this log base 2 of 12 minus 2, if you're looking for an exact answer, you're going to have to solve it by hand anyway. So sometimes it's quicker with the calculator, sometimes it's not. Just weigh your options there, but you have to know how to do it without because you're going to be asked to do it without. I digress. Let's move on to inequalities. What makes an inequality different than an equation? We're still looking for the value of equivalency because that's the threshold, right? But then we need to see which side is larger. So if I'm thinking about two logarithms and what's happening with their graphs, they're going to intersect once. It doesn't matter how the graphs are done. They'll intersect a max of one time. There could be situations where you have logarithms that don't intersect, something like that, where one logarithm is always greater than the other. So you just have to mess around and see what happens. So the first thing I'm going to recommend is if you have something like this, something complicated, and you're not necessarily sure what the next step would be, replace the less than or equal to with an equal sign. So log of x minus 8 plus log 2 is equal to log of 3x plus 4. And then solve this as you would. So log of 2x minus 16 is equal to log 3x plus 4. So 2x minus 16 is equal to 3x plus 4. If I subtract 2x, I get x on the right, and if I subtract 4, I get negative 20 on the left. So I get x is equal to negative 20. So that's where the intersection would occur. Like with equations, we need to test this value, see if this value actually works. And in this case, it doesn't. It fails here, and indeed it fails here as well. So if you get a double failure, what that means is that one side is always larger than the other. So to figure out which one is which, you need to know what the threshold is. We need to look at these domains, and the one with the smaller domain wins. So the domain of this logarithm is x is greater than 8. The domain of this logarithm is x is greater than negative 4/3. So what do I mean by a smaller domain? I don't mean a smaller number. 8 to infinity. Semantics. We're going to get into semantics here. 8 to infinity includes how do I say this mathematically sound? X is greater than negative 4/3 includes some numbers that x is greater than 8 doesn't include. For example, 1. 1 satisfies this inequality and it does not satisfy this one. We need the inequality that is satisfied the least, which would be x is greater than 8. So x is greater than 8 is by default what we have to use. And to see if this is true, this might not ever be true. To see if this is true for the x is greater than 8, we need to test something. Let's test 9. So if I test 9, I'm going to get log 1 plus log 2 is less than or equal to log, I still forgot the 0, or the O, log 9 at x equals 9. 9 times 3 is 27, plus 4 is 31. Multiplication when you add, so you have log 2 is less than or equal to log 31. That is true. So we are going to say that this is our answer. So if we didn't get a true statement there, then it would never be true. So interesting thought there. So they never ever intersect. So we have to use their domains in order to find the answer. So a little bit weird. And if you have questions about it, like, please ask. Next one, we don't have as much of a problem with because there's not 3 logarithms in the equation. How I recommend solving these inequalities is using the one-to-one property with exponentials. So how I recommend solving this is 2 to the power of log base 2 of 2x plus 6 is greater than 2 to the power of 3. Because this is equivalent to this, its greater than or less than values should also be the same. Now, you do have to be careful with these bases. If you use bases like a half, that's decreasing over time, the sign would flip. Because we're using a base greater than 1, it's increasing always over in its domain, so then the inequality would hold. You really do have to think about it. None of these questions are skill and drill. I'm going to do the exact same thing every time, and I'm not going to have to think about it. You do got to think about it, and that's why I like these equations a little bit more than the ones we've done before. So I know that this simplifies down to 2x plus 6. I know that 2 to the third is 8. So then I can solve this inequality. That would be 2 to the x is greater than 2, x is greater than 1. And now let's check to see that x is greater than 1 satisfies our domain. So if I plug in a 1 here, I would get 2 plus 6 is 8 to the power, 2 to what power is 8? That would be 3. So that's good. If I plug in something bigger than 1, let's do 5. If I plug in 5, I get 2 times 5 is 10 plus 16, plus 6 is 16. 2 to what power is 16? 2 to the 4th power is 16, which is greater than 3. So this is good. So again, you got to think about these a little bit more. What about if I just have an exponential? Those were logarithms. Logarithms are weird, Mr. Whaley. Let's do an exponential. Well, we can subtract 4 from both sides. We get 3 to the power of x plus 2 is greater than 23 plus 4, 27. And here's where you have your rabbit hole if you have 2 options, right? 3 to what power is 27 is a very easy question. 3 to the x plus 2 is greater than 3 to the third. So that means x has to be greater than 1. Or you could be like, let's try to use logarithms, because why not? So we know that 27 is greater than 0, and we know that this is greater than 27, so our logarithms should hold. Log base 3 of 3 to the power of x plus 2 is greater than log base 3 of 27. Log base 3 of 27 is 3. Log base 3 of 3 is 1, so we have x plus 2 by the power property, and then we get the same thing of x being greater than 1. So, again, multiple ways to do that one, multiple ways of thinking, great. please just make sure it works. Please think about all the steps you're taking. Don't take them mindlessly. So that is inequalities, and they're not bad. They just take a little bit more thinking than we might be used to for blindly solving equations, but they're not bad. Last but not least is inverses, finding inverses. We've done this before with polynomials and rationals, and we showed before that exponentials and logarithms are inverses. So if you see an exponential and you ask for an inverse and you don't have a logarithm in it, it's wrong. And if you have a logarithm and you ask for its inverse and you don't have an exponential in it, it's wrong. But let's do two of them just for fun. So we have x is equal to 3 times 2 to the power of, it's not x anymore, it would be y plus 1 minus 4. So we're going to subtract 4, x minus 4, and then divide by 3. And that would give us 2 to the power of y plus 1, log base 2 of both sides, log base 2 of x plus x minus 4 over 3 is equal to log base 2 of an exponential. That would cancel, leaving us with y plus 1. Subtract 1, so we get f inverse of x is equal to log base 2 of x minus 4 over 3 minus 1. Not bad. With logarithms, we can do the exact same way. So x is equal to the natural log of 2y plus 3 plus 10. We're going to subtract 10. X take away 10 is equal to the natural log of 2y plus 3. Raise both sides to the power of e. So, no. Raise e to the power of both sides. E to the x minus 10 is equal to, e and the natural log would cancel, leaving us with 2y plus 3. Subtract 3 and then divide by 2. So e to the x minus 10, subtract 3 divided by 2. So we get, it's not f this time, it would be g inverse of x is equal to e to the power of x minus 10 minus 3 all over 2. Not bad. That is it for this lesson. The major thing, the big point to take away is the one-to-one property and its repeated use in these equation solvings. Do you always need it? Kind of. It's useful in every single one of them, even if we don't think about it. Even if we're thinking about we're rearranging an exponential to become a logarithmic, you're technically still just using the one-to-one property. That's why it works. So hopefully this makes sense to us. If we have any questions, that's why I'm here. Make sure you ask. Otherwise, I'll see you in the next video.